These notes are about half-life, just kind of understanding conceptually what's happening. And we are going to do some calculating, but the calculating part's going to be pretty simple. But anyways, just in general, what is half-life? If something's radioactive, it's going to naturally decay to become more stable. And then it takes time for it to decay. So if you look at this graph here, if you start with 100% of the radioactive isotope, once only half of that remains, then like here I only have 50% of the original atoms, then that is my half-life. So for this particular graph, the half-life of that isotope would be about 5 years. So it takes about 5 years for the sample to become half of it will decay into a new daughter isotope, and then half of the remaining will still be the original parent isotope. So half-life, here's another graph there. This is kind of showing you the sample, like the red dots are the radioactive isotope, and then as time progresses, and you can see right here, there's half of the sample remaining. So we have only half of the red original, and then the daughter, the new isotope is represented with gray. So the half-life here is about 1600 years for, what is this? Radium-226. Every different radioactive isotope has its own half-life, and you can see from these tables that, like the polonium up here, the half-life is in 163.7 microseconds, but yet look at uranium-238, it's 4.46 times 10 to the 9th years. So they can really vary on how long it takes for half of the isotopes to decay. And right here, this one is kind of showing you the original sample size is 10 grams. So after one half-life, you'll only have half that remaining. And then another half-life. So in this case, the half-life is right here, and that represents 5.27 years. So after another 5.27 years, another half-life, then you'll have half of the 5 grams, which is 2.5 grams. And then again, after another 5.27 years, you'll have half of the 2.5 to 1.25 and so on. So it kind of approaches zero. So a question that you might have is just interpreting a graph. If you find a sample, or somewhere there was a sample where 50% of the original carbon-14 is still there, but that means the other half of it decayed into nitrogen-14. In this case, you wouldn't have to know that, but it's a beta decay. Anyways, you can see that half of the sample remains at 5,700 years. So that is really the half-life of carbon-14. So if you only have 12% of the carbon-14 remaining, it's much older. You can kind of come over here and see that it's probably about 17,100 years old. There's just two examples I want to go over with you, and they're really simple. Like I said, there's an actual equation, and they can be not always such perfect numbers, but we just want everyone to understand the basics. So if you have a problem like this, where the half-life of phosphorus-32 is 14.3 days, and you know that there's been 57.2 days since starting with a 4 milligram sample, they want to know then how much remains. So the first thing, in order to figure out the number of half-lives that it's gone through, you're going to want to take the total time divided by the half-life time. And again, like I said, our numbers are going to be really nice and work out perfectly as whole numbers. So it is, I think it's 4. Yeah, so we end up that it's going to undergo 4 half-lives. So if it's a 4 milligram sample, after 1 half-life, you'll have 2 milligrams. After another half-life, you'll have 1. Another half-life, so I'm on my 3rd half-life. We're going to have a half a milligram. And then 1 more half-life, and we'll have 0.25 milligrams. So the answer is 0.25. This is another type of problem where if I tell you the amount of total time that passes, so if I have a sample and I'm starting with 80 grams, it undergoes 1 half-life. So only 40 grams of it remain. And then, it just keeps halving until we get to 2.5. So 2.50 grams. So it really underwent 1, 2, 3, 4, 5 half-lives in 27 hours. So the half-life of this isotope is going to equal 27 hours divided by 5. And that would then give the time for each one of those amount in milligrams to decay and half of it to remain. So I get 5.4 hours would be the half-life of this particular element. And that is all I have. One other thing. Sorry, I'm going to talk about a decay series. So a lot of times something that's radioactive will undergo a decay to become something else, and the daughter, it does always have a half-life, but sometimes then that substance that's produced is not stable, so it will continue to decay. So this one's a pretty awesome one. If you're starting out with the parent being the uranium-238, it's going to decay it's an alpha decay, you can see, into the thorium. And it takes, 4.5, 10 to the 9th years for that. Once the thorium is formed, which is the daughter, then it can undergo, here's a beta decay, and it keeps doing this. So the elements have different half-lives and successively keep changing because everything that's produced is still radioactive until you get down to the final lead. So you wouldn't have to be able to write one of these, but just kind of appreciate that once something decays and it takes a certain amount of time for half of it to decay, it forms a new daughter isotope that itself could be radioactive, and then it would then undergo another decay. And that's all I have.